Hello everyone, welcome to the explanation of my project titled Market Price Prediction Model. So this is the third assignment I received as part of Mentorness machine learning internship. Before getting into the technical side of this project, let's analyze the data set that we have been provided with. Our objective is to develop a robust time series machine learning model which is capable of forecasting the market trends based on the historical data. And we have been provided with several attributes such as market, the month, year, quantity of the commodity, maximum price, minimum price, price mode that give the most frequently occurring price of the commodity during each month, the state, city and the date. The first step that we are adopting is data pre-processing, where we handle the missing values by dropping the rows with missing entries. Then we encoded the categorical variables such as market, state and city using one-hot encoding that separate the binary features for each category. And we converted the date column to the datetime format, and we extracted the year and month as separate feature. Then the numerical features were scaled, and this ensured all features are on similar scale. Then target variable price mode was selected, and we split it into data was split into training and test set. Then we conducted the exploratory data analysis, also known as EDA. The first was temporal pattern, where we could see that the line slope upwards from left to right. Although there must be some fluctuations around the trend, we can say there is an overall increase in the trend, then the pattern suggests an upward trajectory. The quantity over date was mapped. And then we saw the trend, that is the long-term upward or downward movement in the data, and in our plot we can see the price has overall increasing trend over the time and is plotted using a blue graph. And coming to seasonality, which refer to the repetitive pattern in the data over a specific period, we can see it does not appear to be a strong seasonal component to the price in our case. And residual, which is the part of data which is left after accounting for trend and seasonality, it appeared to have random fluctuations around zero, though no clear patterns is visible and is spotted using magenta graph. Moving on to the autocorrelation plotting, it helped us to see if a time series data point such as price in our case is related to its past values. And in our plot, the x-axis has a lag value. It shows how far back in time we are looking. For example, a lag of 1 compares the current price to price 1 period before. And y is autocorrelation coefficient, which ranges from -1 to 1. In our plot, we can see the values are close to 0, which suggests no significant relationship between past and current prices. So this can be helpful when we choose a time series forecasting model in our future. Then the next step was feature engineering, where we applied several feature techniques such as lagged variables. Lagged variables are created to introduce the past values of time series as new features, and rolling statistics were included, such as rolling mean and rolling standard deviations are calculated, which capture the moving average and variability over a specified window. Then we did the seasonal indications, such as seasonal component was mapped against date. We can see the Fourier series decomposition was adopted, which is the red line, and it closely resembled the original seasonal component, which is blue line, where we said stability in seasonality was not mapped. But here we suggest there is a presence of subtle seasonality in the data in comparison to the previous time series data we obtained. So feature engineering has enhanced our data as of now. Then we can move on to the model training, where we adopted 3 types of models. The SARIMA model, that is the seasonal ARIMA model, that extends ARIMA by including seasonal components, which makes it suitable for data with seasonal patterns. And then the second model was ARIMA model, that is auto-regressive integrated moving average model. It is used to capture linear patterns in the time series data. Then we have also adopted a profit model, which was developed by Facebook as a robust model for forecasting time series data. It handles missing values and outliers as well. Then we are evaluating how these models have performed. So we can see we have three metrics, that is mean absolute error, mean absolute error, mean squared error, and root mean squared error, where mean absolute error will give us the average difference between predicted and actual value. Squared error will give square of difference between actual and predicted value, and root mean is the root of mean squared error. We can clearly see that Sarima and Arima models perform similarly almost, with a few difference in their percentages, and they achieve lower error compared to Profit model. The Profit model has resulted in higher ME, MSE and RMSE that suggested a larger overall difference between the predicted and actual price values, which we cannot actually rely upon. So we will actually choose Sarima model as it's slightly better than Arima model and has very less error values for MAE, MSE and RMSE. We may either actually fine tune the hyperparameters of Sarima and Arima to potentially improve their performance in future if required. That's all about this project. Thank you.